Look closely at carbon-based molecules like alkanes or benzene rings. They form the structural foundation of organic chemistry, largely because they are naturally stable and resistant to change. That stability creates a hurdle for synthesis. To build complex, useful materials, we have to attach new pieces to these carbon chains, but they lack the reactive points needed to form a bond. The solution is to strip a hydrogen atom and replace it with a highly reactive halogen, like chlorine or bromine, creating a haloalkane. That halogen provides a reactive site, transforming a stable chain into a molecule that actively binds with new structures. Manipulating these reactive sites requires high precision. Chemists rely on name reactions to dictate exactly how these molecules behave under specific conditions. These reactions provide the operational control required to build specific molecular structures on demand. Certain halogens are difficult to attach directly to a carbon chain. In these cases, chemists first build a basic haloalkane and then perform a precise chemical swap. When the goal is to attach an iodine atom, chemists deploy the Finkelstein reaction. Introduction of sodium iodide in a dry acetone environment allows the sodium to bond with the original halogen. As that bond breaks, it clears the path for the iodine to take its place on the carbon chain. Fluorine poses a different challenge. It reacts so aggressively with carbon that direct attachment is difficult to control, making the Schwarz reaction the preferred method for safe attachment. Instead of a direct approach, the Schwarz reaction utilizes heavy metallic fluorides, like silver fluoride. The silver removes the original halogen, while the fluorine transfers over to the carbon chain in a controlled exchange. By utilizing these exchange methods, chemists can produce specialized alkyl iodides and fluorides that would be difficult to create through direct halogenation. Aromatic benzene rings, or haloarenes, require a different approach. Their closed-loop structure is inherently resistant to the substitution methods used on straight carbon chains. To modify the ring, chemists synthesize a highly reactive intermediate compound known as a diazonium salt. Synthesized at low temperatures, the diazonium salt creates a localized point of instability on the ring, making it receptive to a new halogen atom. Once primed, Sandmeyer and Gattermann reactions deliver the final halogen. Sandmeyer uses a copper salt for the exchange. Gattermann uses copper powder and halogen acid. In both, the diazonium group is displaced, allowing the new halogen to bond. Sometimes the objective is to remove the halogen entirely, to fuse two separate carbon molecules together. This fusion process requires sodium metal suspended in a dry ether environment. In the Wurtz reaction, sodium strips halogens from two straight-chain haloalkanes. The exposed carbon ends immediately bind, forming a longer chain. The Fittig reaction applies this to haloarenes. Sodium removes the halogens and fuses two hexagonal benzene rings directly, creating a biphenyl structure. The Wurtz-Fittig reaction joins distinct carbon structures. By introducing one straight haloalkane and one halobenzene ring, the sodium removes both halogens, allowing the straight chain to graft directly onto the side of the aromatic ring. These methods allow for the expansion of molecular size, connecting isolated carbon fragments into larger frameworks. When we look at these reactions together, we see three distinct operational categories: the swappers, the aromatics, and the welders. Names like Finkelstein, Schwarz, and Wurtz represent specific protocols for the deliberate construction of molecules. Haloalkanes and haloarenes provide the starting materials for advanced organic construction. This type of molecular engineering is the standard for chemical synthesis, allowing for the production of complex pharmaceuticals and specialized polymers. These reactions form the baseline for chemical manufacturing, enabling the predictable assembly of molecules for use in modern medicine and industry.